Hello everyone, welcome to our final presentation. We're at Team 9 and we're working on the analysis and redesign of our raclette fondue set. Our raclette fondue set is used for grilling and making raclette, so it's going to heat up various foods for dipping, and it's got an electric heating coil to heat the pans and the pot. For our production volume, we're making 500,000 sets per year and selling them at $120 per set. Our primary customer group is household consumers. It's going to serve families of 4 to 6 people and just need to keep food warm over the course of one meal. Our secondary consumer group is food catering businesses. So this is going to serve larger groups over long periods of time, and it's going to need a larger size pot. Here's an assembly view of our raclette set. For the functional analysis, the main function is to prepare food. It does this by cooking food through adding heat, containing the food, and maintaining the temperature. Our first assembly sequence uses the bottom-up method. You can see the second sequence uses the top-down method. Through our assembly sequence analysis, we were able to determine that the bottom-up sequence works better. Here you can see the function component matrix mapping for each part and then which function they serve in our set. Here's the bill of materials for each part in our assembly, and you can see that the total production cost before any adjustments comes out to about $76. Next is our quad chart. It shows the functional importance of each part along with its manufacturing costs, and then those with a high manufacturing cost and functional importance are suggested for redesign.
Our product family variant serves the secondary customer group, the food service such as caterers for large events, and our variation was that the pot should be larger so that it can increase the amount of food being warmed and served. Here's a functional differentiation table highlighting that the only different function is contain food and the amount of food contained. And then our component commonality table. The pot assembly were identified to be the most effective module to change. And then here's the original pot assembly on the left and then the larger pot assembly on the right. And here's the two screenshots of section views highlighting the common interface, and at the bottom of the larger pot subassembly is the same shape and size as the original, so it can fit in the same spot. And here's our product family design assembly sequence based off of sequence number 1, which identified to be the better of the two analyzed. It's already installed at the end of the sequence, so it's already optimal for the delayed differentiation method.
Here we have the mechanical assembly times for the entire sequence. You'll note that we've highlighted two, the plate and the pot assembly, and these are the ones that are chosen that have the highest cost and highest function and are our platform and module parts. The total system has 56 parts and the efficiency is 217.42. Here you see our platform part, which is the plate. And it goes from having a screw and nut attachment method to having a sliding feature that is on that little adapter plate. Here you can see CAD views as well as some critical dimensions, as well as the design guidelines like reducing fasteners, reducing part count, as well as lowering cost of fits like a sliding or snap fit. We have the same type of drawings here for our plate, where we've also reduced fasteners, and listed critical dimensions important to the part.
For our mechanical assembly modular part, we have our original pot assembly for the primary customer group. It uses 2 sheet metal handles welded to either side, and then for our redesigned, it uses only 1 detachable handle so that the pot assembly can be installed at any orientation. So here you can see the pot assembly without the handle attached, and the tab for the interface is so small that you could rotate the pot assembly any way during installation and it wouldn't obstruct the grill plate. And here's just 2 detailed views of the interface between the pot and the pot handle. And here are the CAD image and drawings for the pot subassembly, and the changes made to it are highlighted in callouts. And then finally, here's a drawing detailing the dimensions of the tab and slot interface and an isometric image of the CAD part for the pot. After our redesign for manual assembly, we found that the pot handling time decreased, the plate insertion time decreased, 2 nuts and 2 screws were consolidated, and the coil adapter plate insertion time decreased as well. In total, these improvements reduced the part count from 56 to 52 and improved our efficiency from 217 to 201.
The design of automated assembly, we have selected a sub-assembly consisting of the base and parts around it, which are the short, medium, and long standoffs and the screws. In the calculation of total handling and insertion costs, the total number of items after redesign decreases to 11, while the total assembly cost reduces by $1.32 from the original sub-assembly. For the redesign of our sub-assembly, we have stuck to the DFA guidelines of reducing part counts and fasteners. The screws at the bottom of the base have been eliminated, as well as the short, medium, and long standoffs. These parts are instead injection molded at the base, significantly reducing our part count. Given below is the comparison of our sub-assembly before and after redesign. Removing the screws omits the need for rotating the base, whereas removing the standoffs reduces the need for different sized parts and easier vertical assembly of subsequent parts. The critical dimensions of the plate have been shown in the front and top view. All dimensions shown in the figure are in millimeters. Here we have the critical dimensions of the base for the front and top view. The dimensions of the injection molded projections have also been indicated here.
Further, the following slide shows the process selection for the modified base and plate. Here is the material shape matrix for the base. The following slide shows the mass and section thickness matrix for the base. This slide shows the process tolerance and roughness matrix. According to our economic batch size of 500,000 and other process matrices, our final candidature process were machining and injection molding. Injection molding was finalized as the candidature process as it was cost effective for the higher production and volumes we wish to manufacture, and also due to the more rapid pace without the need of post-processing. So the process selection table shows the various processes which fail at the different process matrices. And a similar process was chosen for the modified plate. And the following slide show the cost for the redesigned parts, total cost for redesigned parts.
This slide shows the modifications with the DfM Pro. As you'll notice, there are no DfM Pro suggestions for the modified plate, suggesting that our designs were good. You'll notice that our process was the same as the original design for assembly redesigns, so there have been no changes to the dimensions. In the same case, the DfM Pro base also has no design changes for those dimensions, but you'll notice we do have DfM Pro suggestions, such as better standardized wall thickness, adding bosses around some of the post features, and adjusting the height of the ribs to meet the parameter specifications. This is the costs before and after redesign. You'll notice that the plates after redesign goes up slightly in price, as well as the base price. While these prices are more expensive for the manufacturing, you'll notice that our total cost for the assembly goes down. The other thing to note is that the Hub's quote is significantly less than our analytical, and that's most likely because Hub's only quoted to 100 parts, and so the extrapolation for our fit curve is maybe giving us an inaccurate estimate. And these show our Hub fit curves.
Our product service system that we selected was a fondue recipe sharing app called Recipe. So users can record and upload their own recipes, view a bunch of fan favorites that we've already created. And then a cool feature is that they can select how many people they plan to feed, and the app will automatically adjust the ingredients in the recipe. So this helps the environment by reducing food waste and takes the guesswork out of your cooking. As for improvements to our product, so we have the benefits from DFA and DFM, which reduce our total cost by $7.53. So that's about 10% by reducing the number of fasteners that we had. We really liked our modular design as it reduced the grill plate obstruction. However, reducing the fasteners kind of gave up some structural integrity and robustness in our assembly. If we could do a different approach, we'd focus on a broader redesign to redesign the arms that hold onto the grill plate, but when we could only pick 2 parts, that wasn't really possible for the scope of this class. Thank you.